Hello everyone. Today we will continue discussing our topics on synchronous machine. So in the last session, we discussed together the parameters identification of the synchronous machine, and we mentioned that we can do parameters identification by making two tests. One is called open circuit test and one is called short circuit test. And from these tests, we will have the data to draw two curves, the open circuit characteristic and the short circuit characteristic. And from these two curves, we can draw a third and a fourth curves. So a third curve is the air gap line, or is the modified air gap line, and another curve is the air gap line. So we have now four curves. Three are related to the open circuit characteristic, and one is from the short circuit characteristic. How can we use these curves and this data to identify the parameters of the synchronous machine? So firstly, let's agree that for any synchronous machine, we have synchronous impedance, which is the armature resistance and the synchronous reactance. The armature resistance can be obtained using DC test, which is just measuring the resistance across the winding. So this is the equivalent series resistance of a winding, and this is the armature resistance. So this is a very simple test. And from the open circuit and short circuit, we can get the impedance. Once we got the impedance, we can calculate the reactance because RA would be measured using the ohm meter. So this is a way how can we identify the parameters. If we have a large synchronous machine, large means high power synchronous machine, the resistance is mostly neglected compared to the reactance. So we can say that if the armature resistance is neglected, so we can say that XS equals Z. But what is the meaning of unsaturated and saturated? So unsaturated synchronous reactance or synchronous impedance, whatever reactance or impedance, if we consider the resistance or neglected. Unsaturated means we will use the air gap line. So the air gap line means this is something ideal. So the unsaturated curve is ideal. Unsaturated values are ideal values. So we can just calculate the ideal value just to know our impedance, and it's not going to be that exact value. So the exact value is going to be that one we can calculate from the saturation. So what is the saturated impedance? Saturated impedance can be calculated simply using just V divide I in order to calculate the impedance. So which V and which I? So after drawing the open circuit and short circuit characteristic, we can calculate the impedance at the rated value. So at the rated value, so this is a rated volt. You don't need to identify the rated value from the open circuit characteristic because rated value is already known. But you need the curve for the purpose to get the field current at the rated value. So once you know the rated, the field current, which is the current at this point A, once you know this field current, IF at point A, at the same point you can get the value of the short circuit current at rated volt. So this value of IA now is required in order to calculate the impedance. So what is the value of the synchronous saturated impedance? It's nothing but V rated phase divide IA at this point B. So for that, you can find here the relation is ZS saturation equals ECA, so the volt of CA, which means from point C to point A, which is the rated phase value volt, divide IBA, which is the current at the field of the rated volt. So this is how can we calculate the impedance. And again, if we neglect the armature resistance, so this would be the synchronous reactance. This is for the saturated impedance. For the unsaturated, we extend the line of the same field current until intersect with the air gap line. And this would be the voltage magnitude that we can use in order to get the unsaturated impedance. So we can say now the unsaturated impedance is the volt between point DA divide the same current of IBA. So this is the way how can we get the unsaturated impedance. Don't forget that saturated open circuit characteristic, saturation or saturated impedance can be calculated from open circuit characteristic. And open circuit characteristic can be used in case of independent generator, which is not connected to infinite bus. I mean, can be used even during the calculations, not only to during the parameters identification. So for the parameters identification, the saturated value has to be obtained from the open circuit characteristic as we mentioned. But otherwise, during the normal operation of the generator, you can use the open circuit characteristic only if the generator is not connected to infinite bus, which is independent or islanded generator. Also, in the questions, if you find the expression, the generator is disconnected from the infinite bus, so this means it's islanded mode, so you can still use the open circuit characteristic. For the unsaturated curve, the air gap line, this is ideal case, and this is only used for the unsaturated impedance identification. For the modified air gap line, it's used all the time if the generator is connected to the infinite bus. So this is the parameters identification and when we can use these curves that we can see in this graph. Now, let's solve a numerical example together. So in this example, guys, this is the textbook example, number 6.2. So the example says the following data are obtained for a three-phase 10 megavolt ampere. So this is the apparent power is rated. 14 kilovolt star connected. Star means Y connected. So this means the 14 kilovolt is the terminal line value, line to line volt, star connected synchronous machine. And these are the data given here in this table. So as you can see in the first column, you have the different values of the field current. The second column, you can see the open circuit volt in kilovolt, line to line. So this is a measured value, line to line value. So as you can see also, the point here is the rated value, which means this is the current at rated value. This is the field current at rated value. So you don't need to draw the curve in order to identify this value. It's already given in the table. And even you have the air gap line volt at the same value and the short circuit current at the same value. So for the time being, for the parameters identification, I don't need to draw the curves because all data are given at the point that I need to identify the parameters. Okay, let me show you this again on the curve. So what data we have? We have all the data for the open circuit characteristic, and this point or this line is given. So we have the field current, we have the armature current of this value, we have the volt, for sure we have this volt because this is the rated value, and we have also this voltage magnitude. So all the values you need to make the calculations are given in the table, so you don't need to draw the curve for the time being. So let's continue solving and getting the values. And if we need to draw for any other purpose, we will draw the curve. So for the time being, part A, find the saturated and unsaturated synchronous reactance. So simply we can use values we have in the table. So the value of the current is, take care, the value of the current is the armature current. So this is IA. This is IF. We don't need to use IF to make the calculations. All of the time we use the armature current to make the calculations. So the armature, the field current is just indication to the values that we have. So we have the field current at 200 ampere at the rated volt and these values of current and air gap line volt. Okay, guys. So simply we can say that Z saturated equals this volt divide root 3 because it's Y connected. So we need to get the phase value. So 14 kilovolt divide root 3 over the corresponding short circuit current 490 ampere. So this would provide the impedance at saturation. If you would like to calculate the impedance of the unsaturation, so you can use the 18 kilovolt. So you can say 18K divide root 3 in order to be phase value, divide 490. So this would provide the synchronous reactance, the unsaturated value. So as you can see here, guys, here are the curves. So here in the textbook, he draw the curves, and it seems there are some other parts of the question he will need to use the curve, okay? But again, for the parameters identification, we don't need to draw the curve for the time being because we have all the values we need. So Z unsaturated equals 18 kV divide root 3 in order to be a phase value, divide 490. So we have 21.21 ohms. Here in this example, guys, the resistance was given. It's not written right here, but I'm gonna provide the data. So RA equals 0.07 ohm. So resistance was given in this example, okay? So for that, he used Z square minus R square under square root in order to get the value of the reactance. Can you see, guys? This is the impedance. This is the reactance. It's almost the same. Why? Because if you see the rating of this machine, it's 10 megavolt ampere. It's huge power. Okay, so we can neglect the armature resistance in this example, but here the textbook he used the exact solution, so no problem to consider the exact solution. So again, this value of resistance is given. The other value, the saturated value, we can use it as we mentioned, the rated volt divide root 3, divide the same armature current. So the value is 16.5 ohm. Again, the saturated reactance can be calculated using the resistance we have. So it's going to be also 16.5 as you can see. So here is how can we calculate the parameters of our machine. There are other parts of this question in the textbook, okay? But let's focus only on the parameters identification for the time being. Now, we would like to drive the power relation of the synchronous machine. Someone can say we already have the power relation, which is nothing but root 3 V line I line cosine phi or cosine theta. Yeah, this is correct. But this is based on any electrical power or any power system. We need a specific equation for the synchronous machine, depends on the machine parameters. So let's relate the power to the machine parameters of the synchronous machine. How can we do that? Let's start the derivation from the basic definition of power. So you know that the apparent power S equals V times I conjugate. You know also that we assume the volt as a reference, so V terminal is at angle 0, and EF is going to be magnitude at angle delta, and the impedance is RA plus JXS at angle theta. So this is the power factor angle. And this is the power triangle we have. So this is P, this is S, and this is JQ. And the angle here is nothing but the angle theta. This is the power factor angle. Now, we need to make a revision for the power. So let's get the current as a function of the machine parameter. You know, guys, that I equals EF minus V terminal divide ZS. So we can say that IA equals EF at angle delta minus V terminal at angle 0 divide ZS at angle theta. So this is IA. If you would like to get IA conjugate, so this would make the angle in negative. If you do that and substitute here with I conjugate and multiply the current times V terminal, so this would be V terminal divide E times EF divide Z at angle. You know, it should be delta, because here you multiply two vectors, so the angles will be added. And here you have in the denominator, so the angle of the denominator will be subtracted. So it would be 0 plus delta minus theta. So this means delta minus theta. But because we have I conjugate, so this would be theta minus delta. Okay? And minus Vt times Vt, so Vt square. And the angle, instead of being minus theta, it would be plus theta when you take the conjugate of current. So this is the apparent power vector in volt ampere per phase. You know, if it is for 3 phases, guys, we have to multiply times 3 if these values are in phase value, and root 3 if it is line values, okay, in case of Y connection. Okay, guys? So this is a per phase apparent power. You know that the active power is nothing but the real part of the apparent power. So as you can see, if you multiply S times cosine theta, this would give you the value of the apparent power. So doing that, guys, the real part of S is going to be the absolute value cosine the angle. So absolute value here, cosine the angle, so cosine theta minus delta, minus Vt squared divided Z cosine the angle of theta. So this is the real part of the equation. And the imaginary part would be with sine instead of cosine. So these are the active and reactive power relations. Now, if we go back to the definition of the high rating machines and neglect the armature resistance. So if you neglect the armature resistance, so in this case, instead of using ZS at angle theta, it would be, if R equals 0, it would be JXS, which means XS is the absolute value and the angle is 90 degrees. So if you use that and neglect the armature resistance in the impedance in these two equations, this would lead to theta is equals 90 degrees, and cosine 90 minus delta is nothing but sine delta, and cosine 90 equals 0. So the power equation is going to be in 3-phase case, it's going to be 3 V terminal phase, EF phase divide XS instead of ZS, and sine delta. So cosine 90 minus delta is sine delta. So this is now the 3-phase power relation. And doing the same with the reactive power. So replacing ZS by XS and theta S by 90. So this would give you 3 V terminal EF divide XS cosine delta minus 3 VT squared divide XS times 1 because sine 90 equals 1. So this is the Q or reactive power for the three-phase. Now, if you have a look to these relations, guys, specifically for the power relation, this is V times E divide X, which means this is a scalar value, sine and angle. So if you compare that to the sinusoidal waveform equation, you can say that this is the value of the maximum or peak value of the sine wave. So we can say that P equals P maximum sine delta, where P maximum is nothing but 3 V terminal phase EF phase divide XS. And this would be the equation now. So if you draw the curve of the power, this would be the shape of the curve. And I'm going to consider only the angle from 0 to 180 degrees. Okay? And even we will discuss more in deep about the angle. We cannot go beyond the 90 degrees. We will discuss the reason of that. So the curve here, you can see this curve now is the power versus the power angle, delta. For that, guys, we call delta power angle. Can you see? So the power is depending on the variable delta. So for that, we call delta as power angle. We didn't call it excitation angle, for instance. It's still the angle of the excitation, okay? But we call it the power angle because it's more effective in power and giving a huge indication in terms of power. So for that, we call delta as power angle. So can you see, guys, now? The power is going to be maximum if power angle equals 90 degrees. Okay? So this is the curve of power. Now, you know that the mechanical power equals torque times omega. And omega is constant value in synchronous machine. We said that synchronous machine speed all of the time is constant. So in this case, we can say that the torque is going to be the same shape of the power, okay? And the peak value of the torque is going to be P maximum divide omega. So this is the torque relation, P3 phase divide omega. So it's going to be 3V terminal EF divide omega times XS times sine delta, which is T maximum sine delta, where T maximum is 3V terminal EF divide XS times omega synchronous. We have some common names for the operating point at delta equals 90 degrees. What are these names? First name is maximum power, because the maximum power can be obtained at delta equals 90 degrees. Another name is maximum torque, because it's the same. Maximum torque can be obtained at the same angle. Maximum, sometimes we refer to the maximum by pull out. So pull out power or pull out torque, giving the same indication that delta equals 90 degrees. And one thing else is steady state stability limit. Steady state stability limit. What is the steady state stability limit? So we need to discuss more about this point. So now this is the point, and we have 5 names for these points. Let's see what is the meaning of steady state stability limit. Let me write or draw something here in another slide. So I'm going to draw a section for our machine. So this is the axis of the machine, and this is, assume we have pull N here and pull S here. So the flux lines is going to move in this direction. And this is going to be the main vector of our flux. Okay. And your rotor, if the rotor, let me draw the salient pole rotor because it's going to be easier to be understood. So this is, let's say, this is a direct X of our motor. Later on, you will understand, guys, what the meaning of the direct X and the quadrature X. But this is the main X of our rotor right now. So if the rotor, and this is the direction of the flux, if the rotor X is in the same direction of the flux, so this means power angle equals 0. So this means in this case, we do not deliver any power from this machine. If you start loading this machine, what will happen is, let me draw this in with another color. So this is the rotor X in red one. I'm gonna draw the rotor X again if you load this machine. So if I load this machine, for instance, with a certain amount of power, you will find that the X of the rotor is like that. X of the rotor means the rotor is here like that. So this is position number 2. Where is the power angle? The power angle is the angle between the new X to the other X here. So this shift here is representing delta. So this means the flux is going to be stretched from this X to move through the core and return back again to the same X. So the X of the rotor, or the angle or the displacement angle between the rotor X and the flux X, is the power angle delta. What will happen if you increase this angle more? Let's say go to 90 degrees, which means, let me draw that in a different color, which means the new X of the rotor is going to be here. So here, delta equals 90 degrees. Actually, what will happen is the flux lines will be stretched very much. Like that. And any more increase in this angle will make these flux lines are very weak and may be cut. And in this case, we call the machine lost the synchronism. Let me correct that. So the machine lost the synchronism if delta is greater than 90 degrees. Once the delta increased over 90 degrees, but again, guys, sorry, this is not for the salient pool, but I'm just drawing the characteristic like that, or drawing the X like that in order to be understood with you, okay? So this would be actually for the cylindrical pool type. So if delta became more than 90 degrees, what will happen? You will load the synchronism, and the machine will be turned to the instability region. And if you go to the instability region, you have to have a closed loop control for your machine. Otherwise, everything will be broken and you cannot control the machine anymore. So for that, guys, we said steady state, stability, limit at delta equals 90 degrees. For that, it's not allowed to leave the machine loaded until having delta equals 90 degrees because it's very critical. It's very, very critical. So no one can operate the machine at maximum power. This is very tricky point, and the current is going to be very high, almost twice the rated current of the machine. Okay, and we do prefer to keep the power angle in acceptable range, maybe from 30 to 40 degrees at most, so not more than that, to avoid overloading our machine and keeping the machine in synchronism and in stability region. So if we go back here, guys, this is the stability region of our machine. If you would like to have like a simple definition for stability, I'm going to give you like a very small example here. If you have a cup and small ball inside here, and the cup is with this shape, if you make any disturbance for the ball inside the cup here, so it will oscillate a bit and return back to the same place again. So we can say this is a stable system. But can you imagine if the cup is like that, and you have the ball on the top here, and you make a disturbance to this ball? So if the ball moved in this direction, can the ball return back again? No way. So this is an example for the unstable. Okay, so this is just a simple example to understand what the meaning of stability. And in control systems, you will learn the stability and how to make the system stable using closed loop control, using different control techniques like PID controller, for instance. Okay. So again, the maximum power is the steady state stability limit of our synchronous machine. And again, guys, here I just made the rotor in this shape just for simplicity. However, this should be cylindrical type, not salient pole type, because in salient pole machine, actually the angle is not 90. So it's going to be maximum power at 45 degrees if it is a salient reluctance machine. If it is salient synchronous machine, which means you have field supplies, so this is going to be between 45 and 90 degrees. So again, this is for cylindrical type. Okay. If you operate a machine, you would have a constant power condition or control. What is the meaning of constant power condition? So in order to keep the load working, you may have different requirements from the load. You may have different requirements from the reactive power. You may need to change the excitation, and excitation is not changeable automatically. You have to control that. Or if your load is increasing, you need to control the excitation in order to achieve a certain loading condition. So we compare what's called constant power operation. Constant power operation. So what's the meaning of constant power operation? We mentioned that, guys, power is proportional to, it's 3V terminal EF sine delta divide XS. Okay, so let me write the relation firstly. Power equals 3V terminal EF divide XS times sine delta. So 3 is constant. V terminal is going to be constant for the generator connected to infinite bus. XS is constant for the machine. So we can say power is proportional to EF times sine delta. So if the power is constant, EF sine delta would be constant. Let's see the phasor diagram now and see where is EF sine delta. So in case of lagging power factor, this is V terminal. This is IA. So we have IARA if we neglect the resistance right here. So we can say the volt or the equation is EF equals V terminal plus JIA XS. So this is in case of neglecting RA, and we said that this is most probably the case in large synchronous machines. So this is V terminal, and this is going to be JIA XS. So this EF1 is the lagging power factor excitation vector. For this vector, for the time being, we have this vector EF1 is at angle delta 1. So where is EF sine delta? EF sine delta would be this value here, correct? So this is here, this term here represents EF sine delta. So this is proportional to EF sine delta, or let's say equal EF sine delta. For the second case, which is unity power factor, this is IA2. So this is JIA2 and this is EF2. Where is EF sine delta? Still the same. So this is EF sine delta. For the leading power factor, this is IA3 and this is JIA3 and this is EF3. So if you have a look here, this is EF3 and still for the same EF sine delta of EF3 is going to be the same length. So we can say that this line here is the locus of excitation for constant power. So this line represents the excitation locus. Locus means the value of EF is going to be vary across this line for different power factors, okay, at the condition of constant power. So if you have a generator controlled in order to provide constant power, you can say now EF1 sine delta 1 equals EF2 sine delta 2 equals EF3 sine delta 3 and so on. So this is the first condition of the constant power. If you compare two cases, so we can say first case EF sine delta equals second case EF sine delta. Okay, so this is the first thing. Take care that the angle delta, this is delta 1, this is delta 2 up to this line, this is delta 3 up to this line. Delta here is going to be 90 degrees, and this is the maximum delta you can have, which is the region of stability. So for that, you can find here, this direction here represents the unstable region. So here we have a stable region, and here we have the unstable region. Okay. Let's see another condition for the constant power. You know also another relation for the power, which is power equals root 3 V line I line times cosine phi, which is the power factor angle. We can say from this relation that P is proportional to, we said the V is constant, root 3 for sure is constant, so it's IA times power factor. So we can say power is proportional to IA times cosine phi as well. Let's see that from our curve here. This is the first IA. This is the second IA. This is the third IA. And you know that the power factor is the angle between voltage and current. So phi 1 here is the angle between IA and V terminal. For the second current, phi equals 0 because this is unity power factor. For the third current here, IA 3, so this would be phi 3. If you compare the three cases together, you would find that this length here represents IA cosine phi. So IA1 cosine phi 1 is this length. IA2 cosine C0, which is power factor unity, so power factor unity cosine angle equals, cosine angle equals 1 if the angle is 0. So this would be the IA cosine phi in the unity power factor. For the third one, IA3 cosine phi 3 is going to be the same length. So we can say that this line here represents the current locus at constant power factor. And we can say also that IA1 cosine phi 1 equals IA2 cosine phi 2. So we can use this condition, guys. We can use these two conditions if the power is constant. And this is called constant power conditions. Let's solve an example and see how can we use these conditions. Please, guys, I'd like all of you to write notes how to read the example, how to read the problem. So everything in the problem should provide some information. Starting from here, three-phase, 5 kVA, so 5 kVA is S rated of this machine. What is the meaning of S rated? This is the rated apparent power of the machine. Does it mean our machine here is going to work at this power? Or it can be loaded with different value? For sure, it can be loaded with different value. But if it is mentioned that the machine is full load or working at rated, so this means the machine is working at 5 kVA. 208 is the value of the line. 4 poles, 60 hertz, star connected, so star is Y, star or Y connected synchronous machine. So in this case, we can say that this V line is 208, so we can say V phase equals V line divided root 3 because the machine is Y connected. Has negligible stator winding resistance. So RA, from here we can say RA equals 0. And a synchronous reactance of 8 ohms per phase. So from here we can say XS equals 8 ohms per phase, for sure. Any impedance is given per phase. At rated terminal voltage. Okay. So this means the impedance equals these values at rated terminal voltages. And we all of the time keep the impedance values the same or constant within the machine operation because the machine is designed to operate at rated volt all of the time. The machine is firstly operated as a generator in parallel with a three-phase 208 60 hertz power supply. So this means this synchronous machine is connected to a grid of three-phase 208 volts, so the same value, RMS value. We cannot synchronize the machine to another value. 60 hertz, it has to be the same value as well. And the machine is connected in parallel to that source. Part A, determine the excitation volt. Excitation volt is EF. And power angle. Power angle is delta. Actually, EF and delta are the same vector data. So once you get EF as a vector, you would have the magnitude of the volt and the power angle value. So determine these values when the machine is delivering rated kVA. So now we can use the value of 5 kVA because the machine is working at rated kVA and at 0.8 power factor lagging. So this is the power factor status, 0.8 lagging power factor. So we need to find these values, EF and delta, and draw the phasor diagram for this condition. Let's solve part A and then come back to see what is the remainder of this problem. Seriously, guys, you have to know that in order to calculate EF and angle delta, you have to have a loading condition. Loading condition means S and power factor, IA and power factor, or P and power factor. Any of these cases have to be there in order to calculate the value of EF and delta. If you have one of these values and you don't have the other, no way to solve the question numerically. You have to solve graphically. And graphically is solving using phasor diagram. We will discuss later on how can we have a graphical solution for such problems. But let's focus now on the numerical way or the analytical way how to solve the problem analytically. So again, in order to calculate EF and delta, you have to have one of these cases, or let's say the data of one of these, the three cases, which by the end means this is a loading condition. So this is the loading condition. So Here in our question, we have S and power factor. So since we have the apparent power and power factor, we can go ahead and continue solving the question. So we have only one relation to calculate EF and delta. The relation is EF equals V terminal plus GIAXS. Here the resistance is neglected in this question. So this is our relation. So in order to know that, in order to get EF, you have to calculate IA. And you can calculate IA from the loading condition, which is S and power factor is given. So we can say firstly, V terminal is the V phase value. The machine is Y connected, so it's going to be V line divided √3. So this is 120 volt per phase. And the apparent power is 5 kVA. So we can say now I equals S divided √3 times V line. S divided √3 times V line, because you know, guys, that S equals √3 V line I line. This is the general form of the power as absolute value for sure. Okay. If it is vector, so I has to be conjugate. Okay. So we can say now IA equals S divided √3 V line. So this is the value of our current. We don't have the angle. In order to solve in this equation, you have to have the current as a vector. So what is the angle? We can get the angle from the power factor. So power factor is 0.8 lagging. So we can say phi equals minus, because it's lagging, and the angle is cosine inverse the 0.8. So we can say phi equals minus cosine inverse the power factor, which is 0.8 in this case. So this is the angle. Now we can use the current as a vector, 13.9 at angle minus 36.9. Substitute in the equation. Don't forget that all the time V terminal is a reference. So reference means at angle 0. So 120 angle 0, and take care again, this equation is phase values equation. We cannot use line values. So V phase is 120. So 120 at angle 0 plus IA, which is 13.9 at angle minus 36.9. Don't forget, guys, to write the angle. So this is a vector. It's not scalar value. Then JXS, which is 8 at angle 90 degrees. If you calculate that, guys, you would get the value of 206.9 at angle 25.5. Take care, guys. This is generator. And before of getting the result, you have to know that delta has to be positive for generator. So if you got, by mistake, the angle is in negative sign, this means you have something wrong. You have to check again your calculations, because the machine is working as a generator and delta in generating case is positive all of the time. What is the acceptable value of delta? It has to be less than 90 degrees. Otherwise, you still have something wrong, because the machine is working all of the time in a stable region. Okay. So what is the value of the excitation volt now? Since we have the values in the problem in line-to-line values, so you can convert that to line, or if you can say or identify this is a phase value, so no problem. So here, the value of excitation is 206.9 at angle, volt per phase, and the power angle is positive 25.5 degrees, and positive again because this is a generator. Now we calculated the excitation and power angle. Let's draw the phasor diagram. So this is nothing but the phasor diagram in case of lagging power factor. It's not solved here, but let me check here. It's not solved. So let me draw the phasor diagram here with you. So this is V terminal. IA is lagging. So this is IA, and this is the value of phi. So value of phi is 36.9. So I'm going to write just the symbol phi. So this is IA, and RA is neglected. So we have JIAXS. So this is JIA times XS, and this is the value of EF, and we can say this is delta equals 25.5 degrees. Take care, guys, that IA and JXS have to be right angle. Okay, so this is EF, and let's call this EF1, IA1, V terminal. I think V terminal is going to be the same. So JIAX1, delta 1, and this is phi 1, because this is case number 1, our loading condition. Okay, so this is the phasor diagram. Let's see part B. So in part B, he says, if the field excitation current is now increased by 20%, and he wrote, guys, a note, without changing the prime mover power. What is the meaning of without changing the prime mover power? So the input power still the same. So this means our case here is constant power operation. So we can use one of the two relations we mentioned. One more thing, guys, we need to note between lines. Take care that he mentioned here the field excitation is now increased. Is it going to be increased automatically, or you need to increase it? Actually, it's not going to be increased automatically, which means if the load is changed, or if you have any case of changing in your machine, the excitation is going to independently change. It has to change by control. Okay, so it's not going to be changed alone. It has to be changed by control. So now the field is increased means by means of control. Okay, and it increased by 20%. Increased by 20%, this means the new value is 1.2 times the first value. What is needed here? Find the stator current. So we need to calculate IA, find power factor, and reactive kVA, so reactive kilovolt ampere, so the value of Q supplied by the machine. So we need to get these three values, IA, power factor, and reactive power, if the excitation is increased by 20%, and we got that it's constant power operation. So let's see, guys, how can we do that? So we said that for the constant power operation, we have two relations. EF1 sine delta 1 equals EF2 sine delta 2. And IA1 power factor 1 equals IA2 power factor 2. 2 and 1 are referring to the new case and the old case. So he mentioned here that the excitation is increased by 20%. So this means EF2 is 1.2 times EF1. So I can say again, EF1 times sine delta 1 is given, which is 25.5 degrees. So this is equals 1.2 times EF1 times sine delta 2. So EF1 would be omitted from the relation, so you can get now the value of delta 2. So this is the way here, and here is the value of delta 2. Take care, delta also is still positive because this is generating operation. And we need now to get the current, so you have the new value of the delta, and you can calculate EF2. So EF2 is 1.2 times EF1. So EF1 is already calculated in the first part. So here EF2 or EFA referred to here as prime, not 2. So EF prime is 1.2 times the first value of EF. So this is the value of EF in the second case. So simply you can say now IA equals EF minus V terminal divided JXS. Just direct substitution in the relation, and you can get the new value of your current. What can we see here? We see that this is the value of current, and this is the angle. The power factor can be calculated as cosine the angle, so the power factor is 0.62. I'd like just to compare one thing, guys, with you. So the current is still lagging. The first case, the current was lagging as well. When we change or increase the excitation by 20%, what happened to the power angle? So the power angle was 25. The power angle now is 21. Why this happened? Because as you can see, we have constant power operation. You increase the excitation, so delta has to be decreased in order to keep this term constant. So from the calculations, 21 is indicating that we are, or our numbers are making sense. So delta has been decreased because the excitation is increased. Okay. So all of the time, guys, numbers have to make sense in our machine operation. Okay. Regarding the reactive power, so simply you can calculate now the reactive power as 3 V terminal IA sine phi. We have V terminal phase 120. The current is calculated, and sine phi is calculated as well. So you can calculate the, so sine 51 is this value. So you can calculate the reactive power, and the reactive power is 5.03. Okay, so this is part B. Let's see part C together. With the field current as in A, so A means the first case. So this is before of increasing to 20%. With the field current in A, the prime mover power is slowly increased. So prime mover power means the input power. And the input power will not increase without a command from the control unit. We have a load increase and we need to provide more power. So please increase the input power of the machine to provide more power to the grid. So this is what happened, guys, in power generation systems. The control unit contact the generation unit. Please increase the power in the coming few minutes, in order to provide like 10% extra of power, 20% extra of power, like that. So this is coming from the control units. Okay. So once this order is coming to the generating unit, they will start increasing the increasing the generation by increasing the prime mover power. Okay. So here he mentioned that the power is slowly increased. It has to be slowly. So because, guys, if you make like sudden change, this would make some transient or bad transient effect on the machine. So we don't need to make any bad effect on the machine. So we do prefer to have slowly increasing of the power. And the same is also for excitation. So the power is slowly increased. To what limit, we don't know yet. So let's continue and see. What is the steady state or static stability limit? So this question here can be answered even without knowing any data, because we know that the steady state stability limit means the power angle is 90 degrees. So if you would like to know what is the steady state stability limit in terms of angle, it's 90 degrees. In terms of value, so you have the value of excitation, you have the value of volt, you have the value of reactance, so you can calculate the maximum power. Okay, so this part here can be calculated easily. Then, what are the corresponding values of the stator or armature current, the power factor, and the reactive power at the maximum power transfer condition? So here, guys, this part is reflecting one thing that is very important. So the prime mover power is going to slowly increase. But in order to start increasing the power, you have to know your limits. It's not an engineering solution to increase something or decrease something without knowing the limits. Otherwise, you may burn your machine. So, for instance, if you are working in a site and you get a command to increase the power by 20%. So you have to see where are you working right now. Is increasing the power 20% more will make the machine overloading? will reach to the maximum condition because this may burn your machine. So you have to have the sense of the machine and understanding the limits of your machine. So in this case, this question like let you know that don't increase the power without knowing the limits. So this is the purpose of this part of the question. So we need to know what are the limits of our machine. Okay. So simply, let's see now at delta equals 90 degrees, what would be the value of current, of power factor, and the reactive power that we can provide. So starting again, guys, at the maximum power condition at delta equals 90 degrees, so we can say P maximum equals 3 EF phase, V terminal phase divide XS. So 3 times 206.9 times 120 divide 8. So this is the power maximum that we can take from this machine at this excitation condition. So this doesn't mean this is the global maximum power that we can get. No, this is the maximum power that we can get at this excitation value. Okay, guys? Then, what is the value of the current? So simply we can say that IA equals EF minus VT divided JXS. EF is the same value of excitation volt at part A, but this time the angle is 90 degrees. So we can say 206.9 at angle plus 90, and it has to be plus again because this is generator, minus 120 at angle 0 divide JXS. So this would give the following current, 29.9 ampere, and the power factor angle is 30.1 degree. 30 means it's converted now to leading condition. And this makes sense because if you remember that the maximum power for the generator will be at leading power condition all of the time. Okay, this is from the phasor diagram. So the power factor is cosine this angle, which is 0.865 leading. Now we need to calculate the reactive power. So this part is not mentioned here. So you can say again, Q equals root 3 V line, I line, sine phi. So this would be root 3 times V line, which is 208, times I line, which is 29.9, times sine the angle phi, which is 30.1. And you can get the value in kilovolt ampere reactive. Okay, and for sure this is going to be leading reactive power, which means reactive power is coming from the load to the generator. Okay, so don't forget, guys, the meaning of lagging and leading again. So lagging means the reactive power Q is moving from, let's say Q is moving from generator to load. Lead means Q is moving from load to generator. Okay, so this is the meaning of load of reactive power flow in case of lagging and leading. Okay. I think this is enough for today, guys. So we discussed today the parameters identification example, and we solved some questions regarding the constant power. So next class, we will discuss or start in the synchronous motor operation. Thank you so much, guys, and see you in the next class.